Hi everyone and welcome to my presentation. My name is Theo Gargiulis and I'm a research engineer with Unified Streaming. In the next 15 minutes, I would like to present a novel bitrate adaptation algorithm tailored for low latency streaming in the context of MMSys 2020 Grand Challenge on Adaptation Algorithms for Near-Second Latency. The presented algorithm is based on online context optimization, which is an online learning framework. Let's dive into it, shall we? But first, please allow me to make a brief introduction to the current state of adaptive streaming. HTTP adaptive streaming has been the dominant source of data traffic over the past several years, while the demand for multimedia consumption is projected to reach a striking 82% of the global internet traffic before 2022. This percentage is dominated by over-the-top services, while concurrently we are witnessing the expedition of the transition of broadcasting to streaming, along with a multitude of new live streaming applications that give rise to new low-latency streaming requirements. With the advent of new coding and file format schemes, and application layer enhancements, low-latency streaming can now be reliably supported. This is where we fit our contribution with this presentation under the scope of bitrate adaptation, which remains a challenging task, primarily due to channel instability. At the same time, perceived quality of experience, being subjective in nature, often blurs the bitrate adaptation objectives, while latency considerations have only recently been treated more thoroughly, with the immediate requirement for robust, lightweight, and universal solutions becoming increasingly more dominant. More on this soon, but please first allow me to specify how low-latency streaming is facilitated. The video content is encoded in multiple quality presentations, i.e. multiple resolutions to account for the diversity of client devices and multiple bit rates to account for changing network conditions. The content then is typically hosted at a commodity origin server where it is packaged and prepared for transmission to the client. Often a CDN may be involved. By requiring common web infrastructure, we keep operational costs low. Then every encoded sequence is further organized in smaller, independently decodable files called chunks, which can be as small as a fragment. By allowing independent fragment requests, we ensure that the session state is maintained in the case of a failure, and by this data segmentation, we provide finer granularity to the rate selection process, which in turn yields better channel utilization. So at the beginning of a streaming session, the client would typically download an XML file that contains information on how the video data are organized, and then it would deploy a control logic, which is also known as a bitrate adaptation algorithm, which is the main focus of our work here, that sequentially indicates the appropriate bitrate for every fragment, given of course current network conditions. Essentially, the algorithm matches the streaming rate to the channel rate via means of adaptation. This video content organization is in line with the recently proposed Common Media Application Format, or CMAF, which in combination with the supported chunk transfer mechanism of the HTTP 1.1 and beyond, have set the stage for low latency streaming. Our goal is to propose an optimization framework that yields a client-side bitrate adaptation algorithm that exploits these very good streaming properties for low latency streaming. With this short background, I feel confident that we are ready to dive into the detailed specification of our low latency bitrate adaptation algorithm based on online convex optimization, which I remind you is an online learning framework. To motivate our approach further, let me share some insights from previous research presented in MMSys 2017. Existing bitrate adaptation schemes require parameter tuning according to network or application scenario. This presents difficulty in generalizing well beyond a certain scope of usage. Thus, optimal bitrate adaptation, especially over fluctuating channels, remains a challenging and an application-specific operation, while at the same time low latency bitrate adaptation still relies on throughput estimations. To overcome this limitation, recent bitrate adaptation approaches may resort to learning or control theoretical approaches, but their practical implementation may be hindered by energy-demanding architectures, as for instance in the case of deep learning, or by the complexity of exploring the complete optimization space, as is the case in dynamic programming and Markov decision processes. Our proposal is a novel adaptation algorithm based on online convex optimization. OCO emerged in 2003 as a very effective online learning framework that does not rely on estimations, but only on historical values. OCO is model-free, as no assumption for the statistical model of the channel is required, and is independent of any parameter selection concerning the streaming environment. Last, another very good property of OCO is that it provides tractable feasibility and performance guarantees. Let us now formally define the bitrate adaptation problem. We regard bitrate adaptation as an optimization solution to maximize the video bitrate while ensuring stable and continuous low latency streaming. Unfortunately, while bitrate adaptation is indeed an optimization solution, the application of online convex optimization to streaming is not a straightforward task, as OCO requires convex decision space and constraints, while streaming has the discrete decision space, which is the set of available qualities, ergo non-convex, and state-dependent constraints, which are associated with the finite nature of the buffer queue. Thus, in the following, I would like to guide you through our modeling assumptions and a set of relaxations that we had to introduce in order to meet OCO's requirements. First, we model the streaming client by a learning agent who minimizes latency subject to buffer constraints. Essentially, we minimize latency by keeping the buffer short, but in the positive regime. Additionally, we model the channel rate evolution by an adversary who decides the cost of each bitrate decision only after this decision has been taken, thus mitigating the requirement for throughput estimations, based only on historical values. The adversarial setting is general enough to include any potentially time-variant channel rate distribution. The key takeaway from here is that our learning agent minimizes an adversarial loss function associated with latency that is unknown at decision time. We further fulfill the OCO requirements for a convex decision set and convex constraints by a set of relaxations. First, we allow the agent to decide the video quality according to a probability distribution for the appropriate bitrate given network and latency conditions. And second, we make a relaxation to an unbounded buffer, essentially an infinite queue that adheres to time averaging constraints. Let us now specify these two relaxations in detail, and then following we will describe our algorithmic design. Regarding the first relaxation, we convexify the decision space by a randomization operation. The bitrate adaptation process requires the client or the learning agent to select the video quality xt for every fragment t upon bitrate indication rt, which is the output of the bitrate adaptation algorithm. Let us now take an alternative approach. Let us consider a probability simplex omega and use that to learn the optimal probability of choosing xt instead of choosing xt directly. This makes our bitrate decision based on omega t, leaving a convex space. Regarding the second relaxation that concerns the buffer constraints, let me first briefly describe how the buffer evolves in the context of low latency streaming. At every decision epoch, the buffer is updated by the amount of data that has been downloaded and the amount of data that has been played out between consecutive fragment downloads. Thus, by dividing the latest fragment size with the available throughput, we can estimate the amount of video in seconds that has been played out. Typically, the playback rate is constant and equal to 1. Yet, in low latency streaming, the playback rate is allowed to grow for the feed to catch up with the live edge. Every fragment download grows the buffer by a constant value, which is the fragment duration. For low latency applications, this is below 1 second typically. Last, due to memory constraints, the buffer cannot be allowed to grow indefinitely, and thus an inter-request delay may be applied. Thus, the buffer queue is typically constrained below a maximum value in the positive regime. This constraint is what makes the buffer evolution non-continuous and thus a non-convex function. With our relaxation, we treat the buffer as an infinite queue, and thus we allow instantaneous violation of the buffer budget, but we utilize a penalty to maintain the buffer in the 0 to Bmax range on average. With these relaxations in place, we're now equipped with all the necessary tools to formulate an adaptation problem under an optimization approach. Let us define the objective and constraint functions. Ft measures the loss, or even better, the added latency between consecutive fragment downloads at quality xt. Think essentially the time difference between now and the live edge as it is manifested in buffer growth that our algorithm will try to minimize. As we have convexified our variable from xt to the probability distribution omega t, our newly defined loss function ft becomes a random process with respect to omega t. That requires, of course, an expectation. Additionally, the constraint treats the buffer underrun, and thus we define gt as the actual buffer displacement, which in the following we will try to keep in the positive regime. Again, due to the convexification of the decision space, we define the appropriate random process. At this point, a very justifiable question that may have arisen is how can these random processes be meaningful for modeling a discrete problem such as streaming? In the following, we will present an algorithm that keeps track of these processes and respects the constraints on average. And on top, our algorithm enjoys theoretical performance guarantees that are useful in the context of streaming. So we can formulate the optimization problem now via the constrained online convex optimization framework, where we are searching for a bitrate selection strategy that minimizes FT, which is the latency, while keeping the buffer positive on average. And to do so, the following need to happen in succession for every segment download or fragment download. First, the agent needs to compute the probability distribution omega t from the algorithm that we will present shortly. Then, based on that distribution, the agent can select the corresponding quality. Then the adversary will decide the incurred loss of our decision, manifested into added latency and computed by FT, which is possible since after a download, we can compute the download throughput for the particular fragment. Then we can also compute the actual buffer displacement and send all that back to the agent in the form of feedback. One last obstacle that we need to overcome before we disclose our low latency bitrate adaptation algorithm concerns the fact that the constraint function GT is unknown at decision time. Since in adversarial problems, the adversary, here the throughput, is only made known after the bitrate decision has been taken. To resolve this, we apply a prediction operation in the form of a Taylor expansion around omega t based on the previous value omega t minus 1. I kindly remind you that omega t is a probability vector for every available bitrate. We thus can combine all the discussed modules so far into a Lagrangian, which is a function that can be treated as a potential that we want to minimize. L, therefore, contains three modules. The first concerns the buffer constraint function with the appropriate weighting in the form of Q, which is a Lagrangian multiplier that is updated in a dual ascent function as per the term here. The second term in the Lagrangian concerns the latency, weighted by a consciousness factor VL, and last, we regularize our decision by adding the third term, which tries to prevent abrupt bitrate switches between consecutive bitrate decisions. Alpha can be considered as the step size in the gradient descent operation that we will follow next to find where this Lagrangian is minimized. In essence, our algorithm computes the gradient of the Lagrangian and calculates which omega t vector minimizes it. Before we move on to the algorithmic part, I would like to make a note that this modular Lagrangian of our framework has provisioned for multiple quality of experience factors, particularly stalling, latency, and bitrate switching. By minimizing latency and keeping the buffer displacement low, but above zero, we indirectly maximize the average bitrate as sustained by the available throughput every time. This allows for a multi-objective quality of experience optimization that here is tailored for low latency, but constitutes our framework's modular and useful for diverse quality of experience prioritization. And now I would like to present you Learn to Adapt Low Latency, a bitrate adaptation algorithm for low latency that takes a step into the direction of the subgradient of the previously defined Lagrangian. It is a very lightweight algorithm that essentially calculates the probability distribution of the appropriate bitrate in line 2, and in line 3 the Lagrangian multiplier is updated as previously disclosed, and the two operations are repeated sequentially for every fragment of a video sequence. Learn to Adapt has been implemented in Dash.js and is made publicly available for experimentation. I refer you to the GitHub page of Unified Streaming to access it. In the context of the Grand Challenge, we have performed a preliminary experimental evaluation based on 5 network traces provided by the challenge organizers, using a test video sequence encoded at 3 bit rates and organized in CMAF chunks of duration of half a second. As for the playback rate, we have left its selection to the Dash.js player, and in particular in the modified Dash.js software that you can access online. We have made changes only to 2 files of the suite. And here are some experimental results. Due to time limitations, I would like to briefly give you some key takeaways as manifested by our preliminary experimental evaluation. Now, Learn to Adapt Low Latency achieves a relatively high average rate and low latency, which is below 2 seconds. This is obtained by minimal bitrate switching. Low latency Learn to Adapt adheres to theoretical performance guarantees. I refer you to the theorem 4.1 of the paper, and we have experimentally verified this claim. Also in the paper, I refer you to the regret and constraint residual metrics therein. As previously mentioned, our algorithmic approach allows us to adjust quality of experience priorities. In particular, our modular Lagrangian accounts for latency, stalling, and smoothness, which is the frequency and severity of the stalling events. But we should mention here that, of course, all these are a matter of trade-offs, which is typical in multi-objective optimization, which is the case of quality of experience optimization in streaming. And as we have reached the end of this presentation, please allow me to conclude. We have presented and learned to adapt low latency and novel rate adaptation algorithm, which is based on online learning that does not require any modifications according to the application type or any statistical assumptions for the channel. Our proposed algorithm performs well in a wide spectrum of possible network and application scenarios and thus is robust due to its design principle, its ability to learn. Our modeling allows parameter selection according to user-specific quality of experience prioritization, while it facilitates effective bitrate adaptation in low latency mode when combined with CMOF and chunk transfer. All these properties are significantly relevant to the field of modern HTTP adaptive streaming, where over-the-top streaming providers and broadcasters are continuously expanding their services to include more diverse user classes, more network scenarios, and streaming applications such as low latency live streaming. Thank you all for your attention, and I welcome any question, comment, or remark either at the live Q&A session of MMSys 2020 or offline at my email address shown here. I wish you all the best. Thank you and goodbye.